when we were working with the slopes of tangent lines to a parametric curve, what we noticed is that any place you see dy or dx, you can actually rewrite this in terms of t. But there were lots of different geometric calculations we have made so far this quarter that involved integrals that had dy and dx in them. So for any of those, we could rewrite them in terms of a parametric curve. So here's an example. Find the area under one hump of this cycloid. So, you know, anytime we had a graph, all we did was, you know, whatever our bounds were, to find an area, what we did was we integrated f of x dx. But the reason that we were integrating f of x is because, right, this was a graph of y equals f of x. So the reason that we were integrating f of x was because the height of this slice is y, which was f of x. So what we were really integrating was y dx. But this looks like something we could write in terms of a parametric curve. So the area under a parametric curve is the integral of y dx. So let's use this for this particular example. So for a cycloid, the area under the cycloid is the integral of y, which is 1 minus cosine t, times dx, and x is t minus sine of t. So right, remember this differential here. When I write d of something, what this means is the derivative of t minus sine t with respect to t times dt. So this is the integral of 1 minus cosine t, and then the derivative of t minus sine t is 1 minus cosine t dt. Okay, we're going to need some bounds, so what we need to do is figure out for the cycloid what t values give us one hump of the cycloid. So remember, a cycloid looks like this. And for the way this, so we need to figure out when is the y-coordinate 0, because that's, right, these two spots that we want, these are where the y-coordinate is 0. So looking at the y-coordinate, when is this 0? Well, the first time this is 0 is when t is 0. And the next time, right, the next time that cosine turns out to be 1 is when t is 2 pi. So this right here is 2 pi. So we would need to go from 0 to 2 pi. So at this point, we've rewritten this integral that was originally in terms of x and y. We've rewritten it in terms of our parametrization. So now we can temporarily forget about where this integral came from and just work on it like any other single variable integral. So let's see, 1 minus cosine t, so integral from 0 to 2 pi. Looks like we're going to have some powers of cosine. So if we multiply this out, we get 1 minus 2 cosine t plus cosine squared t dt. And then to integrate the cosine squared part, we need to use a trig identity, right? We can use a double angle identity. So cosine squared is 1/2 1 plus cosine 2t, lots of parentheses here, dt. So integral from 2 pi, from 0 to 2 pi. So here we have 1 plus 1/2, so that's 3/2 minus 2 cosine t plus 1/2 cosine 2t. All right, now we can write down an antiderivative. So this is, antiderivative is 3/2 t minus 2 sine t, and then plus 1/4 sine 2t. So I get an extra factor of 1/2 because of a little u substitution that I have to do to handle that 2 right there. Okay, and this is going from 0 to 2 pi. Now when I plug in 2 pi and 0, the only term that survives is this 3/2 t when I'm plugging in 2 pi. So 3/2 times 2 pi, so that's 3 pi. So the area under that, that one hump of the cycloid is 3 pi units of area. Let's look at a little variation on this theme. Let's find the area to the left of this parametric curve for t values from 0 to 2. So we haven't talked about the area to the left of a graph before, but if you think about calculating, so it's this region here, if you think about calculating this region, slicing it vertically would be a mess, but if we sliced it horizontally, right, that looks pretty clean. When I say clean, what I mean is the right-hand end of each slice is on the graph and the left-hand end is on the y-axis, so it's nice and tidy, right? You don't have one end or the other switching between different curves. So all we need to do is add up, integrate the area of each slice. So what is the area of a slice? Well, the width of a slice is just the x-coordinate of this point here. So the width is x, and the height of a slice, well, a slice is infinitely short, so the height is just dy. So what we'll do is we'll integrate x times dy. And of course, our t values are going to go from 0 to 2. So this is actually very similar to finding the area under a graph, which was integral of y dx, but to the left of a graph, it's x dy. Now that we have this integral written down in terms of x's and y's, we can switch to t's. So x is the x-coordinate function, t squared minus 2t plus 2. And then dy, remember dy is dy dx, no, dy dt times dt. So dy dt is 2t, and dt is dt. And now we have an integral all in terms of t that we can evaluate. So to evaluate this, it looks like it's a polynomial, so we can just multiply everything out. First, let's pull this 2 outside, I guess. So then we get 2 times the integral from 0 to 2 of t cubed minus 2t squared plus 2t dt. So our antiderivative is 1 over 4t to the 4th minus 2/3 t cubed plus t squared from 0 to 2. When we plug in 0, we get zeros, so let's plug in the 2. So we get 4 minus, let's see, 16/3 plus another 4. So 2 times 8 minus 16/3, so 24/3 minus 16/3 is 8/3, so 2 times 8/3, so 16/3 altogether. All right, so that's this area to the left here. This is 16/3.